the last speaker today will be Pavel. So he will continue with the previous talk. Right? Yeah.
Okay, so let me just summarize what the upshot is in the first lecture. So I talked about 3 manifolds. So let's say M is a closed range of 3 manifold. And then you can look at this character stack. So the representations of the fundamental group. Of the conjugation. This is this decreasal structure that I mentioned last time, but not so relevant. Right now. And whatever kind of gadget this is, maybe possibly data. So the thing you need to remember from all this is that this allows it to construct an actual sheaf on this stack. So kind of a better version of the constant sheaf. So the constant sheaf is not, because this is singular, the constant sheaf is not a perverse sheaf in this case, but that there's a nice perverse sheaf on the stack. And then you can consider its homology. And so that's an invariant of a 3 manifold. So you start with a group and a 3 manifold, and you can compute this homology. And so let me just recall that this is a very strong. It has a lot of structure. So for instance, this has a structure of mixed. It's mixed. That's mixed structure. We can talk about weights. It also has an automorphism, which is called monodromy automorphism. If you're familiar with the sheaf of vanishing cycles, the sheaf of vanishing cycles has a weight filtration, and it also has a monodromy automorphism, so you can talk about that as well. So very little is known about this this cohomology. Let me just maybe briefly connect to the talk of Sergei Lukov earlier today. This is kind of an algebra geometric version of what Sergei mentioned as this Buffalo-Witten homology of M, where I believe that you compare G to be SL2. And so he talked about this space in terms of analysis of some PDs. This is an algebra geometric version of this space. Okay. So
I just quickly ask you, so you mentioned this rank 9 for the skein module and rank 10.
Yeah.
So can you comment on this?
Maybe not just yet, and possibly maybe even after the talk. We'll get somewhat technical. Okay. So let me just maybe begin with some easy example where this can be easily computed. So probably one of the simplest examples of 3 manifolds is length space. So whatever this is, closed already 3 manifolds with fundamental group singular group over P. So you can see that if you want to understand the character stack, you're looking at order P elements in G after conjugation. So that's something quite explicit. Let me just write it down for GLN. Say G to be GLN. And then this character stack, the length space, you can split this into a union, disjoint union. Like this. My song. So I'll read it in a second. Yeah. Okay, so if they order P elements in GLN, so that they're all diagonalizable matrices, so you can diagonalize those, because you're just looking at conjugation, and then because we have something of order P, all the diagonals have some recursive each recursive unity. So that's why you just need to specify which unity you're considering. This is what these numbers do. How many roots of each of given type there are, and then you just put it there somewhere.
So what is the V?
Oh yeah, sorry, yeah. So when we get there, okay. So that's what the elements are, and then if you look at a given matrix, it will have automorphisms. So if you have a matrix, if there's one kind of root unity, it will look like this. Then there's some other root unity. If it look like this. So that's how the matrix looks like. There's 0 and 1 and so on. If you look at the stabilizer of this matrix, it will be GL2 cross GL3 cross whatever the other blocks are. And so this is what I'm recording here. I'm recording what the morphisms of given matrix. So this is the classifying stack. So this is point 1. The G means stack which is point 1. This is just the automorphism of the crystal. Okay. All right. So this is the this is quite explicit. And then you can ask, what is how does the decreasal structure look like? What is this reverse sheaf? Well, whenever your stack is actually a smooth stack, so this is just a point mod by group, and everything here is smooth. The group is smooth, and the point is smooth. This reverse sheaf likely doesn't come. So the combination of the cohomology just boils down to conjugation of group cohomology of GLN, which is quite explicit. Okay, so in this case, there's nothing much, nothing really interesting going on. Okay. And maybe let me just remark that because the length is the PT length space, maybe just to remind you, in Q or co-prime. But you see from the expression, it doesn't involve in Q. So this answer does not depend on G. This invariant is quite weak, that it doesn't see, of course, different P lattice spaces will give rise to different homologies, but it will not depend on G. Whichever is G. Okay. So let me mention one more piece of structure here. So what you can see is that if you look at the GLM character stack for things, what you see is that it kind of combines character stacks for lower GLMs. For GLMs with a bit smaller m. So let me just explain this kind of behavior. And this is quite general. Let me say this is quite general, and then I'll repeat. Okay, so let's say G is as before, which is not an reductive group. And just think G is GLM. And so let's say T is a parabolic subgroup. And think G, so it's a subgroup in G, so in this case it's GLM. Let's consider the following one. If you look at two blocks, there's a whatever here, and there's a 0. So this kind of block one subgroup. And then let's say L is what's called the Levy subgroup. Again, for this parabolic, this is the group of log diagonals. Yes, so you can just think of, so this Levy subgroup is just product of GLM 1 plus GLM 2, where N1 plus 2. Yeah. So there is a certain result that is expected to be true, which is known in this field as a choice conjecture. So we'll not take this choice conjecture. There's work by several people on this at the moment. But the implication in this particular case is the following: that there's a natural map. This is explained in our paper with Florian Naef. There's going to be a natural map from the homology for the smaller subgroup, so the Levy subgroup, to the homology of the bigger group. Okay, so why is this useful? Well, it allows you to get some information about the homology of the big group from knowledge of homology of smaller groups. So it kind of allows you to compute things inductively. But another thing that it allows you to do is to get what's called a cohomological Cohomological structure. So this is what we concentrate on the case of GLM. So this, let me just take a little bit of this example, G is GLM, and the Levy subgroup is GL1 plus GLM2, where they have those numbers set up to M. And so in this case, this allows you to get a kind of multiplication map. This homology for different ends. And so what we see that if you just combine all those homologies for different ends together, you're going to get the gradient algebra. The gradient algebra in this context is known as cohomological Donaldson-Thomas. This is one constructional way to organize the different homologies together. So at the very end of my talk, I'll mention some I'll mention some versions of this where this is known. Okay, are there any questions so far, or I'll switch to some topology.
So what is it in the lens space case?
In the lens space, this is something quite easy. It's some symmetric algebra with some generators. Yeah, it's probably something that. So because when it's some of all ends, so that you look at the Chern-Simons in no conditions like this, and then you want to do this homology. So that's probably symmetric algebra on the group homology of HTLF. Something. So let me explain the relationship between these kind of invariants of 3 manifolds and more classical invariants, the ones that are already appeared in Sergey's talk. So he mentioned this notion of skein models. I will just repeat the definition. So again, let's say M still goes for the 3 manifold G's a group was 4. So in this case, you can define a certain models. Let's just say so it's based on vector spaces which depend on skew. I'm being a little bit precise. Actually, it can be some root of Q that you need, but not some same models. And for G SL2, this was introduced by Fitz and Drive. Now, this repeat the dynamics that there is in Rousseau. Yeah, so in the case of SL2, it's quite something that's quite explicit. So you consider a vector space spanned by isotopic class list of framed unoriented links. Embedded in M, modulus of relations. Okay, so the first relation is that if you see the unlink, so the unlocked, then you can replace it by this expression times nothing. So if you see a component which is just the unlocked, then you can remove that component at the expense of a factor that involves a q. And the second relation is that if you see a crossing, you're allowed to the powers like this. Yeah, and if you see a crossing, then you get e to the 1/2 times 1 kind of resolution, plus q to the -1/2 times the other resolution. Okay, so this is just something extremely explicit. This was originally, this kind of diagrammatics was used by Kaufman to give an alternative definition of the Jones polynomial. But then you can also look at links in the 3-manifold. Okay, so in this way you get some vector space, which is the skein module. Okay, now what's the relationship between that and this cohomological Donaldson-Thomas invariant? So let me say it is a conjecture, but it's a conjecture that we formulate that sort of part that is already proven. So if you look at the top cohomology of this sheet, I will put a decoration and not explain what this decoration means. Some technical thought about what do you mean by cohomology of the sheet and stack. But you look at the top cohomology, and the claim is that what you get is actually the same model. So let me just parse this. So the same model involves this variable q. So let's just look at using some power series in a bar and a bar some formal variable, according to the Laurent series in a bar. Okay, so this is going to be some vector space over this field of Laurent series. And then this is the cohomological DT invariant, which is a vector space of C in this tensor with Laurent series, and you get this as more. Okay. So let me let's give an example of this, where you can just see, where you can do both sides and see that they're the same. And it's maybe not the most trivial example, so it's useful. So let's just look again at the case of line spaces. And let's look at the group being SL2. Okay, so again, the character set of the length space. So here you look at order 3 elements in SL2. So what do they look like? Well, they look like some rooted unity, zeta. Because of the determinant condition, the other is going to be zeta inverse. So that's how these elements will look like. Okay, so there's going to be two cases. If P is 2, so that corresponds to RP3. You're looking at second roots of unity. So they is either 1 or -1. And so the stabilizer of those will be everything. So those elements are in the center. There's going to be 2 points. And if P is not 2, then what you're going to get is, well, there's going to be a trivial 1 corresponding to data equals to 1, and then a bunch of others. Okay, so you just go over all possible P roots of unity, so all non-trivial P roots of unity, but then you also remember that you can conjugate this matrix to the one where you exchange data and data inverse. There's only half of those in here. Okay, so the top cohomology will just count the components in these stacks. There's 2 components in the first stack, and there's equals 1 or 2 components in the second one. So, and basically that you can see that sorry, I mean the dimensions. You can see that exactly coincides with the dimension skein model. So the skein models were considered quite early in the history. Skein models by Costa and Schicketzin. Let me say a few words why we expect this result, and namely how we're proving this. Okay, so this invariant is completely canonical in 3-manifolds, but to compute it, it might be useful to choose some extra structure on hand. For instance, Hager splitting, like in Sergey's talk. Let's choose this Hager splitting. We're going to write my closed 3-manifold as a union of 2 handle bodies along some Riemann surface, some surface of G. And so, and 1 and 2, you can think of that as the interiors of the G surface embedded in 3. These are the handle bodies. With boundary sigma. Okay, and basically the Hager splitting allows you to give a nice description of the character set, which is useful for combinations. Namely, you can write it like in following form. Write it like this first. the L1 plus L2 over S mod D. And what are L1 plus L1, L2, and S? So here, S is the e to the power 2d, and this has also calculated generics or yeah, you just think of as a slightly manifold, and L1 and L2 are two quantities. There is more to this G form. Okay, so then you get this nice nice interpretation that whenever I apply quality the same so you look at your character stack is written as intersection to smooth Lagrangians, also the multiple. Okay, actually, if you only care about this called homology, you can ignore this multiple group. This will not contribute anything. Okay, so that was that this expression, this homology group, is just some group you can extract from the Lagrangian intersection. So this is some algebraic version of the homology group of these two Lagrangians. These are algebraic Lagrangian manifolds of this simplicity manifold, and this is a Florian. Now, okay, this is one side. Now let me explain the other side, the same model. Turns out the same model has very similar description. Namely, on the skein model side, there is some algebra. So this is an algebra. And this algebra is a deformation. So this has a Poisson structure that can consider differential quantizations. And this is a differential quantization that is manifold. Then there's skein models of the antibodies. This algebra is a quantization of Lagrangians. And then there's a theorem that Sam Gunningham, Jordan, that you can write the skein model at least for generic parameters, like you work over CH bar, as a tangent product of these two. So then, if you want to prove this kind of isomorphism, you can use the finger splitting. and you have one side which is this one-dimensional group, and the other side is in terms of the current factorization, and what we're proving is that the current factorization coincides with this model. Okay, maybe I will say the last sort of main, the last interesting thing about this cohomology. So let me concentrate on the following case. Where the 3-manifold is a Riemann surface cross its one. So again, this is appeared in Sergei's talk. And let's look at the character stack of this. So if you think about what are local systems, or what are representations of the final group for M, you can actually write this in a very nice way. You can write this as the inertia stack of the character stack for the Riemann surface. So if you think what is a local system on a 3-manifold M, which is the product of sigma plus 1, well, it's a local system on sigma plus an automorphism. Well, okay, so this is something you can do. This doesn't yet help you to compute the cohomology, but there's a closely related space you can consider. And so basically, instead of an automorphism, I can consider an endomorphism. So I'm just going to write this as a tricky tangent space. Also identify the cotangent character stack. So this again parameterizes local systems on sigma plus an endomorphism. Again, when I'm writing things like that, there's underlying character stack. Plus, on top of that, there's a decreasing structure which you can read off from derived geometry. Okay. Now, okay, so these are very different. One of them involves automorphisms, one of them involves endomorphisms. But actually, if you ignore the fact that these are stacks, then they're the same. So if you restrict, so let me make 2 remarks. So first of all, if you restrict, if you don't look at all representations of final group, but only look at the reducible ones, well, they don't have any non-trivial automorphisms, and they don't have any non-trivial endomorphisms. So actually, these two will coincide on that locus. So if you're just restrict to reducible representations, you get the same answer. So really, the difference comes from the complicated locus, where you look at reducible representations, where you have some interesting automorphisms. Okay, so the second remark. So why is this relevant or easier? You can actually compute the cohomology of the sheaf here in terms of classical algebraic geometry, or in terms of more classical algebraic geometry. So this cohomology actually can be reduced to just the usual cohomology of the terms, or maybe more precisely, Baron homology of the terms. Now, Baron homology of the character stack has been studied quite a lot. So there were by Pavel Safronov, many follow-ups to that. And so this homology coincides with this Berg additive versions, where you look at endomorphisms rather than polymorphisms. So informally speaking, this is some kind of multiplicative version of this Berg form. Okay. Okay, so this still doesn't tell you how to approach this one, but you can use the following idea. And so this is work in progress by my student Florian Naef. Namely, let's just look at the case of Johan. In this case, there's something nice that happens, that you can look at the exponential map from the Lie operator to the group. And this exponential map, well, first of all, it's surjective. And it's actually an Ital map generically. So there's a system of locus you can write down of matrices where this is involved. So actually, there's an example map from this additive version to the multiplicative version. And using the differential map, you can transfer information you already know on the left-hand side to the right-hand side. So let me just make it even more concrete. Let's look at a surface, which is just two torus. So let's look at the manifold being three torus. So something nice about this example is that a lot of things are known about, for instance, skein models. So Sergey mentioned that computation of the same module result 2, which was 9-dimensional, for instance. More recently, this is the field of Maton vector evolved. And more recently, sorry, this is and so there's an upcoming paper of Gunningham with around Yang. Where they compute actually all these dimensions for SLN and DLN. There's a lot of information you know in this case. So in this case, you can actually compare these numbers to the cohomological curve sheet. So let me explain what's going on with this cohomological curve sheet. First of all, let's understand the character stack. What is the character stack? Well, we call it the fundamental group of T3. That's just D3. So if you look at representations of this group into G, that means you look at 3 commuting elements of the computation. So this is something quite explicit. Again, let me consider the case GBPLM. So you look at 3 commuting matrices of computation. And let me do this trick by replacing everything with not necessarily invertible matrix. So let's look at a version of the space where you look at 3 commuting n-by-n matrices. And now this space is much easier to understand. So both of these will be different to loci, but this one we don't know locally that's different to loci. For instance, for this one we know that it's globally a locus of some very explicit function. Write it down. So there's a function on the space of 3 matrices of the computation. We just take these 3 matrices to the trace x times commutator of y and z. So we can do relatively quickly is to see that if you look at a critical locus of W, we just need to look at convergence of each matrix. You get equations that tell you that these matrices. That's the back. And so once you have this critical description, you can actually compute homology what this it doesn't use the cohomology of the feedback for this event. Right, so this is something you can do. And let me just explain some algebraic description of this. There's a very, very nice algebraic description of what this homology is. So this let me do the following. So this is some fact. You will get using matrices of conjugation. But let's look at the corresponding corresponding states. So in this case, the force moduli space is very explicit. It just means you can remember, so you have three conjugate matrices, you can remember their eigenvalues. You have n diagonal matrices, and there's three of them. So this course moduli space, the space that parameterizes eigenvalues, these matrices, is going to be the n-symmetric power of C3. So there's a map that takes these three matrices and just remembers their eigenvalues. Well, you can do something even better. Let's just combine all of them for all n's. Now, if you look at this combination of all these symmetric powers, well, you get symmetric algebra on C3. And in this case, this homology of the river sheath has a very nice description. Or let me state this. This is the theorem between Davidson and Weinberg. Or a particular case, it's a more general theorem. That describes this push forward. So basically, instead of describing the full homology, you do this sort of partial push forward, and then you can take this homology. So there's a slightly more refined description of this homology that I'm about to state. Basically, it's a symmetric algebra. Some constructible sheet on this complex phase. Whenever I say algebra, there's some natural kind of convolution type analytical structure coming from just adding points. So if you think about Mn, that's n points in C3. So you have n points and n points, you can get n plus n points at the beginning. So this gives rise to whatever some kind of structure in this category. It's like algebra sheet. And if you get sheet, it's just a constant sheet on the diagonals. Mainly, there's a C3 managed in sim M3. Again, in endpoints in C3, and there's locus where all endpoints are the same. This is what I mean by diagonals. and that is the concept. So that gives you a very nice a small version of this homology, and you can, of course, take homology of the whole thing again. Right. And so this working formula that I mentioned is that you can transfer now this knowledge, which is about this case of frequenting and matrices, which are not necessarily invertible. Using the exponential method, you can transfer it to the case of frequenting matrices which are invertible, where you don't have a suitable description. And so surprisingly, this indeed matches these combinations of the same models. Okay, so let me stop here.